Unspeakable. Like knocking my camera over. Why is it? Yeah. I do need to adjust a little bit. Let's see. A little bit less.
Why you want me?
Well, we'll just go with that.
It's shaking.
It'll stop eventually. It'll stop being wobbly eventually. All right, so I know how much you love math in chemistry. So when you hear the word geometry, you're like, no, I hated geometry, all those proofs. Well, molecular geometry is not mathematical geometry. It's not so much sines and cosines. It can be, but it's not in this class. So molecular geometry is how a molecule looks in real space. So yesterday you had your SNATMS kit, and you made various molecules and how they looked in real space. So molecular geometry assigns names to these shapes. Okay, and it's based upon this idea that, once again, electrons are negative and they're going to repel each other. So a bonding pair of electrons creates what's called a domain. And an unshared pair of electrons creates a domain. So if I make my molecule of methane, pretty much the simplest thing, it's just a single carbon. And how many valence electrons does carbon have? 4, because it's S2P2, so 4, it's in group 14. If I make a molecule of methane, which is CH4, it looks like this. And the reason it looks like this is the bonding pair that connects to the hydrogen, connects the carbon to the hydrogen, wants to get as far away as possible from the other 3 bonding pairs that connect the carbon to the hydrogen. So you have 4 bonding pairs, 4 sticks, that in 2 dimensions look like this. So if we draw the Lewis structure of methane in 2 dimensions, it looks like this. You're like, hey, I recognize that. I made that a billion times. But in 3 dimensions, it looks like this, where each one of those domains wants to get as far away as possible from all the other domains, because opposites attract, but likes repel. So this domain repels this domain, repels this domain, repels this domain. So the idea we use is called VSEPR. VSEPR is a fun acronym, and each of those things represents something in chemistry. We'll start with the easy one. What do you think the E represents in VSEPR? Electrons. Electrons. And what do the electrons do? What's the R in VSEPR? Repulsion or repel. And electrons, boom, there we go. Electrons always come in pairs, so electron pair. And which electrons are doing the repelling? The valence. So VSEPR is valence shell electron pair repulsion theory. And it basically says this: domains are formed from bonds or unshared pairs, and they repel each other. That's the bulk of VSEPR. The domains repel each other. Unshared pairs are domains, bonding pairs are domains, and those domains don't want to be near other domains. So they just repel each other in real space. Couple wrinkles. If you have a double bond or a triple bond, the double bond and the triple bond still act as a single domain. Any bond is one domain, double, triple, or single, and then unshared pairs are each one domain. Remember, bonds are made by 2, 4, or 6 electrons, so each bond is a domain, each unshared pair is a domain, and then they just arrange themselves in real space. They just try to get away from each other as much as possible. Dusty. All right. Some of you are still scribbling. I'll give you 30 seconds. Scribble some more if you want. I know how much you like to scribble.
Big scribbler.
Big scribblers in here. If you have any questions, now would be a great time to ask. If you don't have any questions, we're moving forward. If you're ready to move forward, give me a thumbs up. If you have a burning question, wave your hand around. And off we go. What is love? Okay, so we look at Lewis structures. We draw our Lewis structures. We look at the Lewis structures. We look at the bonds in the Lewis structures. And we look at the unshared pairs in the Lewis structures. And from that, we get what's called a fundamental or electronic geometry. If you have two domains opposing each other, they're going to get as far away from each other as possible, and they're going to create this linear geometry, where one domain goes that way, and one domain goes that way. Two domains, linear geometry, 180 degrees away between each other. That makes sense. It looks linear, right? Linear geometry. Or linear geometry. If you have three domains, they will attempt to get away from each other as much as possible. And what happens is they make like a Mercedes symbol, where each domain is 120 degrees away from each other in a single plane. That is called trigonal planar, because it makes a triangle plane, trigonal planar. So if you have three domains, they orient themselves 120 degrees away from each other, trigonal planar, in a plane, in a triangular plane. So that's 3, trigonal planar. Why do you have 10 on you? Oh, that's weird. Probably bumped into something in my pile over here. My big old cleaning up pile. Okay, anyway, so there we go, trigonal planar. Now the most interesting one is the one I was showing you earlier, like methane. When there are 4 domains, the geometry is called tetrahedral. Now you've actually heard the word tetra if you've ever played video games. Yeah, they're like that Russian video game that came out before you were born called Tetris, where the blocks fall. Tetra means 4. Yeah, tetra means 4. So this is tetrahedral. In a tetrahedral geometry, all 4 domains are trying to get away from each other as much as possible. They're repelled. And they are 105 degrees apart. Each domain is 105 degrees away from the other domains. And again, in 3-dimensional space. Now, in 2-dimensional space, this is a 2-dimensional representation. It is okay, but in reality, we're talking about 3-dimensional space, where all 4 domains are 109.5 degrees away from each other. If you have 5 domains, they form 2 triangular pyramids on top of each other. So this is a model with 5 domains. You can see there's a triangle pyramid up here and a triangle pyramid down below. There's like boop, 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 triangle pyramid, boop, 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 triangle pyramid. So if you have 5 domains, we call it trigonal bipyramidal. 2 triangle pyramids, trigonal bipyramidal, 5 domains. Now, 6 domains does not make a hexagon. If you have 6 domains, 6 vertices, then you make 2 4-sided pyramids on top of each other. A 4-sided pyramid on top of a 4-sided pyramid, top of a 4-sided pyramid, that makes an octahedral configuration. 4-sided pyramid, 1, 2, 3, 4. 4-sided pyramid, 1, 2, 3, 4. So a 4-sided pyramid on top of a 4-sided pyramid is what you get with 6 domains. We call that octahedral. Octahedral. Not to be confused with hexahedral, because that doesn't make any sense. There isn't a hexahedral. Well, there's octahedral. And the octahedral domains, they're 90 degrees away from each other. Okay. Lastly, the trigonal bipyramidal is kind of a goofy one. The trigonal bipyramidal is 5 domains, 1, 2, and then 3 around, so it makes a triangle pyramid on top of a triangle pyramid. These domains are further labeled axial and equatorial. Take a wild guess where the axial domains are. Top and bottom, exactly. Like there's an axis that runs to the Earth, so there spins around. So the top and the bottom are the axial domains, and the ones that go around the outside are the equatorial domains. So in a trigonal bipyramidal configuration, you've got 3 equatorial domains and 2 axial domains. All right. Those are our 5 fundamental geometries. Got a really cool simulation. Okay. If you're picking up what I'm putting down, give me a thumbs up. If you have a question we need to address, wave your hand around. Because we're about to add the next layer. Next layer? Now, a molecule may have bonding pairs or unshared pairs. For instance, water, our favorite water molecule, you've got oxygen that has 2 unshared pairs and then 2 bonding pairs. By the way, I've graded the worksheets in the lab so far. If you got something wrong, the first thing you want to check is, or if you didn't get any points or something, first thing you need to check is, do I have all the unshared pairs present? And then did I show my polarity? Because on the unit test, which is going to be the day after you get back from Tuesday, week from today, you're going to have to do three things. You're going to have to draw the molecule's Lewis structure. Then you're going to have to determine its polarity, nonpolar, or draw the dipole. Then you're going to have to name its geometry. Well, here's the deal. Both water and methane have how many domains? 4. So methane's got a domain there, a domain there, a domain there, and a domain there. Water has a domain there, a domain there, a domain there, and a domain there. Okay? 4, 4. They both have 4 domains, which means electronically, they both have a tetrahedral geometry. So far, so good? But you made water. You took a red, which was oxygen, and you attached to it 2 whites, which are hydrogen. That and that look very different, right?
Yes. It looks like
Well, it turns out the domains you do not see are the unshared pairs. A molecule can have all bonding pairs or some unshared and some bonding, as in the case of water. So what we care about is the molecular geometry. The molecular geometry of methane is also tetrahedral. Electronic geometry, tetrahedral. Also, the molecular geometry, tetrahedral. However, water's geometry is not tetrahedral. How would you describe this? How would you describe this shape? Really, that's a word you frequently use? I would describe that as trigonal. Okay. How about bent? Is it kind of bent, like a boomerang? Yeah, like your elbow. You bend your elbow, kind of like you bend the molecule. Well, water has a bent. Let's see if I can put it up here.
That'd be silly.
Oh, I felt like I almost could.
Maybe it will.
I'll give you 5 more seconds. Oh, okay. Maybe on top of here. I like to stack stuff.
I think that's like.
Yeah. Okay, so water has a bent geometry because if we ignore the unshared pairs and focus only on the bonding pairs, it looks like an elbow. And elbow geometry was already taken in pasta, so they went with bent. So what we do is we take our electronic geometry and we further separate it into molecular geometries. If you have 3 domains, everything here that has 3, 1, 2, 3, yeah. So if you have 3 domains, and all of those domains are bonding, then your molecular geometry is trigonal planar. If one of those domains is unshared, then your molecular geometry is bent. Just like with tetrahedral, yeah, like tetrahedral. So 3 of 3 trigonal planar, 2 of 3 bent. Can you see the difference? This is more like AP level right here. One of the things you discover as you explore this is that unshared bonding pairs exert more repulsion than bonding pairs. Unshared non-bonding pairs exert more repulsion than bonding pairs. Also, double and triple bonds, while they're still one domain, they exert a little bit more repulsion than a single pair. But yeah, anyway. All right, if you're ready to move on to the next one, give me a thumbs up. If you have questions, wave your hand around. All right. 4. So if you have 4, you have a tetrahedral fundamental geometry, or electronic geometry. If you are 4 of 4, like with methane, then your molecular geometry is also tetrahedral. 4 of 4, also tetrahedral. If you pop one off, you're like, hey, now there's only 3 of 4. It makes a triangle pyramid. So if 3 of 4 are bonding, your geometry is called trigonal pyramidal. Triangle pyramid. Trigonal pyramidal. Classic trigonal pyramidal. Ammonia, NH3. Here's ammonia. You bait it. So ammonia is NH3, and it's a trigonal pyramidal molecule because there are 4 domains, hydrogen, 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 unshared pair, but the molecular geometry only cares about where the other bonds are. Hydrogen, hydrogen, hydrogen. Trigonal pyramidal. And then once again, water has 4. 2 of them are unshared and 2 of them are bonding. So if you have 2 of 4, you be bent. If 2 of your 4 domains are bonding, you have a bent geometry. Here's the box. There's the box. Question, David.
So is the vent always just gonna have the two bonds, and then no matter how many unshared pairs you have, it doesn't really matter as long as you have the two, it's gonna be vent?
The 2 of 4. So 2 of 4 or 2 of 3 will be bent.
Okay.
So I think the answer to the question you're asking is yes, but when you get to 2 of 5 or 2 of 6, then things are different.
Okay.
But if you are 2 of 3 or 2 of 4, then yes, bent. 2 of 5 and 2 of 6 will be different. Does that sufficiently address your question?
Yeah, that's what I was wondering. Thank you.
Other questions? All right. You might have noticed that 3 domains had 2 geometries, 4 domains had 3 geometries. Guess how many 5 domains has? I would think, yeah, okay. So if you have trigonal bipyramidal geometries, I got one in here somewhere. Yeah. So if you got trigonal bipyramidal geometries, once again, we have axial domains and equatorial domains. If all 5 are bonding, then your molecular geometry is also trigonal bipyramidal. By the way, if you on a test say triangle bipyramid, I'm not going to mark you wrong. Okay. If you don't make it an adjective, that's okay. Like, I think of it as pyramids. If you say top and bottom pyramid, is that okay? I'll be like, no. But if you say bipyramid, I'll be like, yes. Now, if you lose one, the one you lose, the domain that becomes an unshared pair, is one of the equatorial domains, pop, and your geometry becomes seesaw. The molecule exploded. Seesaw.
That wasn't very
Okay, anyway, the molecule there we go. The molecule becomes seesaw. Okay, so if 4 of 5 are bonding, you have a seesaw geometry. The next domain you lose is also axial or equatorial, and then you get this shape. What does that look like? A T. So if 3 of 5 are bonding, you get T shape. T shape. And then if you lose all of your equatorial domains, linear. Linear. 180 degrees, linear. All right, how are we feeling so far? If you're comfortable with this, I'm going to move on to number 6. Give me a thumbs up. Okay. Girls in front are furiously scribbling, so give them another 30 seconds to scribble. All right. Finally, if you have 6 electronic domains and all 6 are bonding, then your molecule is octahedral. And octahedral, because it has perfect symmetry, doesn't really have axial or equatorial domains because it's got perfect symmetry. Just that. So if you remove one of your domains, so 5 of your 6 are bonding, boop, you make a square pyramid. So we call that square pyramidal. Pyramidal. We had to give an adjective because we had to give it an adjective. So the domain is a square pyramid, so we call it square pyramidal. if you lose one. Now here's where things get kind of interesting. If you were to lose another one, which of these domains is being repulsed the most? The top one. This top one up here is being repulsed by 4, but all the other ones are only being repulsed by 3. So the next one you're going to lose is boop, the top one, and we call this square planar. If 4 of 6 are bonding, our geometry is square planar. Should be another page. I'm going to Q4 to make sure. Oh, no, okay. Just a summary. And then if you lose another one and 3 of 6 are bonding, you're back to that shape. What's that shape? T shape. So 3 of 6, you're back to T shape. What do you think it looks like if you got 4 of 6? Sorry, 2 of 6. If 4 are unshared, we're back to linear. Yeah. So 4 of 6, square planar. 3 of 6, I'm a T. 2 of 6, I'm linear. All right. How are we feeling about this? Cool. I almost dropped it again. The whole thing. If you have a question about this, now would be a good time to ask. If you are comfortable moving forward, wave your hand around. Sorry, give me a thumbs up. If you're comfortable moving forward, give me a thumbs up. Okey-doke. Oh, there we go. Here's our summary. Vesper yoga. So again, linear is just linear. Trigonal planar might be, they say angled. This must be European or Australian or something. Might be linear, might be bent. Tetrahedral might be trigonal pyramidal or bent or linear. Trigonal bipyramidal might, notice we didn't say biphonosoidal. We're like, let's just call it seesaw. Let's just call it seesaw.
Thank you.
So trigonal bipyramidal might be seesaw, might be shaped, T-shaped, might be linear. Octahedral might be square pyramidal, might be square planar, might be T-shaped, might be linear. Cool? All right. So, yep, there we are. Okay, so this is what I need you to do. This is for the candies, of course. These are the 3 things that you will do on next week's test. You will be given a molecule. You will draw it properly with all the unshared pairs and bonds proper. You will determine geometry, the molecular geometry, and you will determine polarity. So take 20 minutes or so, or not, maybe 10, 15 minutes, and determine each one of these. Oh, by the way, I put on your notes, or on my comment, a couple of people. That is not nitrogen. And that is not hydrogen. Okay. That's hydrogen, that's nitrogen. This is not chlorine. This is chlorine. Okay? Comfortable with this? Yeah. No. Good. Bad. Good.
Yeah.
Loser.
A lot of people agree.
Okay, it's
Bottom good.
Sarah.
Okay. Capitals are better. All right. So go ahead and do your work.
Okay.
I don't need you anymore. Hey, bye.